Welcome to the chapter on atoms to minerals. The first part will just be on atoms, and I suspect it will be a repeat. Oh, thank you out there in the headphones for reminding me to start my clock. I suspect the first part of this will be a repeat for any of you who've been through basic chemistry before, but we do need to cover it. I apologize. Here we go. I don't know, I just thought it was kind of cute. Either the bird can't read or it's just a rebel. Okay, when you're done with this chapter, actually I have two sets of objectives in here. You're going to be able to tell the difference between a rock and a mineral. Given several items, you'll be able to tell whether or not they're a mineral. Describe and use 8 tests for minerals. Describe 8 ways you use minerals in your daily life. Identify 16 minerals by name using simple tests. Explain the problem with using color as the only test for a mineral. Put common minerals into major families. List the most common elements in Earth's crust. And explain how your life would be impacted without mining. Here is another set of objectives, and these are a lot more detailed. You can look at these under the objectives in the chapter. Okay, first, the atom. Here is our model of it. Our model may be wrong, but it seems to work for now. All matter is made of compounds or elements. Compounds themselves are made of elements or atoms joined together. Atoms of every element, or each element, are identical in size, mass, and other properties. One carbon atom is exactly the same as another carbon atom. Atoms of different elements are different in size, mass, and other properties. An atom itself, and this is where Dalton had it wrong, cannot be subdivided, created, or destroyed, because we now know we can split them apart. When we do, well, that's what the sun does, and it's kind of destructive, unless you're 93 million miles away, in which case we put up solar panels and get the energy from it, which is kind of cool. You can combine atoms of different elements in simple ratios like 1 to 2, 3 to 7, 2 to 5 to 3. In the case of sugar, 6 carbons, 12 hydrogens, 6 oxygens. And you get compounds, but they join together only in certain ways. In the same way you can take nuts, bolts, and various parts and make a car. And in chemical reactions, atoms are combined, separated, or rearranged, and the only thing that's involved is the electron on the outer shell. We now know of, well, kind of this many elements. We are up to, I think, right about here. These are planned but not named because they're being created in cyclotrons or other atom smasher type things. The smallest atoms being up here, the largest ones being down in this part. Here is an overview of the periodic table. The periodic table lists the symbol for an atom. In this case, it is carbon. It lists the atomic number. The atomic number is the number of protons in the nucleus. Now, because an atom has to be neutral, if it has 6 protons, it also has to have 6 electrons. 6 protons, 1, 2, 3, 4, 5, 6 electrons. You may ask, why are the electrons arranged this way? The first shell can hold only 2, the next shell can hold 8, the next shell can hold 8. Wonder if that's on here anywhere. Take a look at this row, 2. Take a look at this row, 8. When you get over here, neon now has a full shell, and any electron beyond that has to go in the 3rd shell. Argon has a full shell. Any electron beyond that has to go in the 4th shell. You get the idea. The mass of an atom is under here. Now, this is a little bit weird because you can't really have a mass of 2.11, but this is an average. Let's say you have a school for people that weigh 110 pounds. And one day, somebody goes out to Taco Bell and has 14 tacos, 5 burritos, and, don't ask me why, 6 large drinks, all with sugar. And they come back and they're 111 pounds. And you average the weight of all your students, they're going to be a little bit more than 110. That's the same way with carbon. There are carbons out there who have an extra neutron. Oops. Now, a neutron has a great mass, but it doesn't change what the atom is. It's the number of protons that determines what the atom is, remember. So, even though that one student comes back a little heavier, it's still a student at your high school. If there's a carbon with an extra neutron, it's still a carbon because it has 6 protons. Now, the mass number is the number of things in here. In the case of a normal carbon, it's 6 protons and 6 neutrons. In the case of carbon-14, it is 6 protons, I hope I said that right, 6 protons and 8 neutrons. but it's still carbon because it has 6 protons. Okay, how do you get molecules out of atoms? Well, here is a cute little frog or a water molecule. Here's hydrogen and here's oxygen. Here is sodium, which is positive, and chlorine, which is negative. They start stacking up like building blocks. Here's what happens when you stack up chlorine and sodium again and again. You get salt crystals, cubes. Here's what happens when you stack up oxygen, has a -2 charge, and silicon with a +4 charge. You end up with what's called a tetrahedron, and that forms the basis of a lot of geology. Here's what happens. Hydrogen, let's go back a few slides, is right here. It has only 1 proton and therefore 1 electron. It would like to have 2 electrons in its outer shell, or it would rather lose 1, because atoms like to have full outside shells. I know that's weird to say, but just deal with it. How can hydrogen get a full outside shell? Well, it could steal an electron, but then whatever it stole it from might not be happy. Take a look at oxygen. It's got 2 in the first shell, and normally it has 6. 1, 2, 3, 4, 5, 6 in the outside shell. It wants 2 more to be full. What does it do? Well, here's what happens. What happens if hydrogen shares one of its electrons with oxygen, and another hydrogen shares one of its electrons with oxygen? Oxygen then has 8 in its outside shell, and it's happy part of the time. Hydrogen has 2 in its outside shell, and it's happy. Because they're sharing their outside or valence electrons, this is said to be a covalent bond. And that's how water is formed. Can you break it apart? Sure. You run electricity through here, gets these guys confused, and the hydrogen breaks off. We can then use that hydrogen to burn in cars, jets, or something like that. Here's an ionic bond. In an ionic bond, instead of sharing, something else happens. Here's sodium. Atomic number 11. It's got 2 electrons in the first shell, 8 in the second shell, and just 1 out there in the third shell. To be full, it can either gain 7 or it could lose this one. Here's chlorine. 2 in the first shell, 8 in the next shell, and then 7 in the next shell. It needs 1 more. I wonder how it could be happy and this guy could be happy. What happens if chlorine simply steals this electron from chlorine? It now becomes negatively charged because it's got 1 more electron than it did before. And sodium, which loses its electron, becomes positively charged. They're then very strongly attracted, and this creates a molecule called sodium chloride. Now, the cool thing about sodium chloride is you start with sodium, a metal, which will spontaneously burst into flame if given a choice when dropped in water, and chlorine, a green poisonous gas. You combine them and we get sodium chloride, this little cubic crystal, which we put on our food. It's neither a metal nor a gas, and it isn't poisonous. Let's go back and look at a covalent bond. You start with hydrogen, a gas, oxygen, a gas, and you end up with water, which we used to put out fire, started by hydrogen. Kind of weird. Now, a bit on mixtures versus compounds. If you throw a pencil and a pen together in your backpack and shake them around, you have a mixture. You haven't combined them. In a compound, you either steal electrons or you share electrons, and you make a brand new material with different properties. In this case, you got apples and oranges. Even if you put them, no, apples and apples. Even if you put them all in the same car, you still have apples and apples. You haven't made some new material. Now, when you start doing all this combining, we end up with minerals like these. Halite, which you eat. Potassium feldspar, which makes the plates on which you put your food. You guys know it as, well, what do you know? It's China. Quartz, the glass you look out when you're bored in your classroom, assuming you have windows. Gold, which your teacher wears all the time. Not really. And copper, which used to make our pennies. Now, silica tetrahedrons, I'm going to cover over this really quickly, and it's not a super big deal, make the bases of olivine, pyroxene, hornblende, ethyl, biotite, muscovite, mica, quartz, and feldspar. These little molecules made out of 3 oxygens and 1 silicon are the building blocks. And if you look closely at a granite countertop, which contains feldspar, the pinky colored thing, quartz, which is clear, but it won't look clear because it's showing the color of the stuff behind it, and biotite mica, which is black, tetrahedrons. Now, on occasion, water gets between these tetrahedrons and makes them flake off. Why does that happen? Water is really kind of cool at binding at things, and you end up with clay when this happens. And clay is an example of a tetrahedron that has been weathered. Here's what happens if you put a bunch of carbons together in a really tight bond. You end up with this stuff. If I mention how to get extra credit, no, I guess I won't do that. Okay, isotopes. Really quickly. Hydrogen normally has 1 proton and 1 neutron. Like I said before, with the students that were all 110 pounds, every once in a while you get a hydrogen with a little bit more weight. In this case, it's hydrogen 2. It's still hydrogen because it has 1 proton. Here's tritium. 1 proton, 2 neutrons, but it's still hydrogen. Tritium, by the way, was one of the gas triggers for the early atomic bombs, and I used to work in a building in Los Alamos where the tritium was stored for those bombs, right behind my building in a tunnel beneath Los Alamos town itself. A little bit weird. What are the most abundant elements in the Earth's crust? This is kind of crazy. You wouldn't think it. By number of atoms, the crust is 60% oxygen. How can that be? Let's go back to this. The silica tetrahedron. Oxygen, 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 silicon. And most of the crust is made of silicates, things of oxygen and silicon, which makes the second most common element silicon. Now, these are fairly light elements, which is why they're on the crust. Remember when we talked about the layers of the Earth? The really heavy elements went down to the center of the Earth. The lighter elements, they're floating on the top, which is why the continents are where they are. The continents aren't going to sink into the Earth any more than the styrofoam sinks into the pool. These guys are light. Let's keep going down the list. Oxygen, silicon, aluminum, and iron all together make up almost 90% of the crust of the Earth. These 4. And if we spell them out, O-S-I-A-L, and iron, which is Fe, it spells Osi Alphi. Don't ask me, it's just something I came up with. But this is kind of crazy. 4 elements that you wouldn't think of making up the crust of the Earth are the most common. Oxygen, silicon, aluminum, iron. Let me say that again. Oxygen, silicon, aluminum, and iron. This is kind of crazy because back in the World's Fair, I think of 1900, maybe it's 18 something, people did not know how to extract aluminum from the earth very easily. So they made a large ball on top of a building out of pure aluminum. And it was worth a lot of money because it was so rare. Now, we throw it away. We probably shouldn't. Don't throw it away. If you see it in a trash can, recycle it, please. Same with iron. Silicon, we use for our solar panels and in glass. No, it's not what goes in other things. I'll just leave it there. Whoop, that is just so cute. Minerals make me happy. I love minerals, and this is how I feel when I talk about it. I love that picture. Going down the list, you also have calcium, sodium, calcium, sodium, potassium, and magnesium. All other elements in Earth's crust, only 3.3%. So when you want gold, when you want lithium for your batteries, for your phone, you're going to have to be very careful about grabbing that stuff. Okay, let's stop on this happy picture.